Hello students, I am Subhashish. Children, you must have studied circles in your lower classes. Well, does the topic circle make any sense without pi? Absolutely not. Also, Euler's number is used extensively in logarithms and algebra. Well, what are these pi and e? Yes, they are known as the irrational numbers. Geometrical calculations involve irrational numbers. So, let us study irrational numbers and the properties of irrational numbers in detail. Learning outcomes. To know more about irrational numbers, to understand the important theorem of irrational numbers. Keywords from this lesson: numbers, rational numbers, irrational numbers, integers, addition, subtraction, multiplication, division, prime numbers, contradiction. Irrational numbers. Before studying irrational numbers, let us define rational numbers. A rational number is of the form p by q, where p is equal to numerator, q is equal to denominator, where p and q are integers and q not equal to 0. So, irrational number is a number that is not rational, which means it is a number that cannot be written in the form p by q. It cannot be written as the ratio of two integers. Representation of irrational numbers on a number line. Here the irrational number is root 2. So, if we calculate the value of root 2, we get root 2 is equal to 1.1412 so on. The numbers go on into infinity and do not ever repeat and they do not ever terminate. It cannot be written in the p by q form where q is not equal to 0. The value that we get is actually non-terminating. Also, there is no pattern in the digits after the decimal. These kinds of numbers are called irrational numbers. Now consider root 3. On calculating, we get root 3 is equal to 1.7320 so on. So, the pattern that we get is non-terminating and non-recurring. So, root 3 is also an irrational number, but in the case of root 9 is equal to 3. This is a rational number. The square root of any perfect square will always be a rational number, and the square root of any number which is not a perfect square will always be an irrational number. Irrational numbers have a decimal expansion that never ends and does not repeat. The most famous irrational number is pi, which is equal to 3.1415, so on. Pi is used to calculate the ratio of the circumference of a circle to the diameter of that same circle. It has been calculated to over a quadrillion decimal places, but no pattern has ever been found, and so it is an irrational number. The few digits of this pattern look like 3.1415, so on. A few examples of irrational numbers are pi, e and phi. E, this is equal to, this is Euler's number and also an irrational number. The first few digits look like 2.7182, so on. Phi, this is an irrational number. The first few digits look like 1.61803, so on. Addition and subtraction of irrational numbers. The result of an addition of irrational numbers need not be an irrational number. 2 plus root 3 plus 4 minus root 3, which is equal to 2 plus root 3 plus 4 minus root 3. Plus root 3 and minus root 3 will get cancelled. After adding, we get 6. Here 6 is a rational number. So the result of adding two irrational numbers is not an irrational number. The result of subtraction of an irrational number need not be an irrational number. 5 plus root 2 minus of 3 plus root 2, which is equal to 5 plus root 2 minus 3 minus root 2. Cancelling plus root 2 and minus root 2, we get 2. Here 2 is a rational number. So the result of subtracting two irrational numbers is not an irrational number. Multiplication and division of irrational numbers. The product of two irrational numbers can be a rational or irrational number. Root 2 into root 3 is equal to root 6. Here the result is a irrational number. The result of the division of two irrational numbers can be a rational or irrational number. Root 2 divided by root 3 is equal to root 2 by root 3. Here the result is an rational number. Theorem: given p is a prime number and a square is divisible by p, where a is any positive integer, then it can be concluded that p also divides a. Proof: using the fundamental theorem of arithmetic, the positive integer can be expressed in the form of the product of its primes, as a equal to p1 into p2 into p3 into so on into pn. Where p1, p2, p3, pn represent all the prime factors of a. Squaring both sides of equation 1, we get a square is equal to p1, p2, p3 into so on into p1, p2, p3 into so on. According to the fundamental theorem of arithmetic, the prime factorization of a natural number is unique except for the order of its factors. The only prime factors of a square are p1, p2, p3, so on, pn. If p is a prime number and a factor of a square, then p is one of p1, p2, p3, so on pn. So p will also be a factor of a. Hence, if a square is divisible by p, then p also divides a. For example, 7 is a prime number and root 7 is irrational. The above statement can be proved by the method of proof by contradiction. In the method of contradiction, to check whether a statement is true, we assume that the given statement is true. We arrive at some result which contradicts our assumption, thereby proving the contrary. Example: prove that root 7 is irrational. Assumption: root 7 is rational. Since it is rational, root 7 can be expressed as root 7 is equal to a by b, where a and b are co-prime integers and b not equal to 0. On squaring, we get a square by b square is equal to 7. Which is equal to a square is equal to 7b square. Hence, 7 divides a. Then there exists a number c such that a is equal to 7c. Then a square is equal to 49c square. Hence, 7b square is equal to 49c square. By simplifying, we get b square is equal to 7c square. Hence, 7 divides b. Since 7 is a common factor for both a and b, it contradicts our assumption that a and b are co-prime integers. Hence, our initial assumption that root 7 is rational is wrong. Therefore, root 7 is irrational. Let us see another example. Show that 5 minus root 3 is irrational. Solution: we will use the contradiction method to show that 5 minus root 3 is an irrational number. Let us assume that 5 minus root 3 is a rational number in the form of p by q, where p and q are co-prime and q not equal to 0. Five minus root 3 is equal to p by q. Add root 3 on both sides. Then we get 5 minus root 3 plus root 3 is equal to p by q plus root 3. Cancelling minus root 3 and plus root 3, we get 5 is equal to p by q plus root 3. Now subtract both sides p by q. Then we get 5 minus p by q is equal to root 3. By taking LCM, we get 5q minus p by q is equal to root 3. Since we already know that root 3 is an irrational number, therefore 5 minus root 3 is an irrational. Points to remember: a rational number is of the form p by q. P is equal to numerator, q is equal to denominator, where p and q are integers and q not equal to 0. The square root of any perfect square will always be a rational number, and the square root of any number which is not a perfect square will always be an irrational number. Given p is a prime number and a square is divisible by p, where a is any positive integer, then it can be concluded that P also divides A. Thanks for watching.